Hello everyone. Today our team Neural Nerds will present on the traveling salesman problem, or in short TSP, and compare it with different search techniques like DFS, BFS, IDFS, and hill climbing. These are the content of PPT, and you can find them in the respective pages. So the traveling salesman problem is very simple to state. A salesman needs to visit a set of cities exactly once and then return to the starting city. The challenge is to find the route that minimizes the total travel cost or distance. TSP is not just theoretical. In logistics and supply chains, it helps delivery trucks choose efficient routes. In airlines or taxis, it reduces travel costs. Even in network and circuit design, TSP helps optimize wiring and layers. So it's a real world problem with big impact. Let's talk about a small example problem. So let's take four cities A, B, C, and D. The distance between cities are given in a table. From this, we can calculate possible tours. For four cities, there are only six tours which we can actually check manually. But imagine if there are 10 or 20 cities, the number of possible tours grows extremely fast. That's why solving TSP is difficult. We can represent TSP as a search problem. The variables would be the order of cities. The domain is all the permutations of the cities, and the constraints are the city can be visited only once, and we should return to the start city. In the search view, a state is a partial path. The initial state is the starting city. The goal test is when all cities are visited and we return to the start. The path cost is just sum of distances. So solving TSP means nodes are partial tours. Actions are extending the tour by choosing the next city. The goal is completing the tour with minimum cost. Now let's see how different algorithms approach this. So for DFS, we go deep into one path. Pros, simple, requires less memory. Cons can take every like very long because it explores blindly. For BFS, it explores level by level. The process guarantees the shortest path in terms of number of steps, but the cons are uses a lot of memory and time grows exponentially. IDFS and hill climbing, let us talk about them too. In IDFS, it is a mix of DFS and BFS. Searches with a depth limit, then increases the limit gradually. The pros are it uses less memory till complete. Cons still exponential in time. Hill climbing, a heuristic or local search method. It improves the path step by step. For example, by swapping cities. Pros, it is very fast, but the cons, it may get stuck in your local optima, meaning it doesn't always find the best path. The complexities of DFS, BFS, and IDFS are of n factorial. Uh, so we can say it goes extremely fast. That's why they are accurate but not practical for large city numbers. But for hill climbing, the time complexity is O of k dot n, where k is the number of iterations. It's much faster and uses very little space, but it doesn't guarantee the optimal solution. So these are the results and performance of each algorithm. So let us discuss about the results. For Sorry, DFS, BFS, and IDFS are exact algorithms. They will eventually find the best path, but they're too slow for large problems. Hill climbing is fast and works well for larger city sets, but it may miss the best path. So there is always a trade-off between accuracy and efficiency when it comes to the algorithms. So in conclusion, for small city sets like 6 to 8 cities, we can use DFS, BFS, and IDFS, which will be practical because the time it takes doesn't bother that much. But for large city sets like 10 or more cities, exact methods become impractical because of factorial growth in those cases. Hill climbing and other heuristics are preferred as they give quick and good enough solutions. Thank you. Now let me explain the Python code we wrote to solve the traveling salesman problem using DFS, BFS, IDFS, and hill climbing. For each algorithm, we see how it's implemented, then compare performance. At the top, we imported libraries like math, sys, random, time, and DQ for BFS. This line here, it increases recursion depth so DFS and IDFS doesn't crash. This class TSP solver DFS solves TSP using depth first search. We start from one city and push it into a stack. Each element stores the current city, visited set, and cost. When all cities are visited, we add the return cost and check if the path is cheapest. Otherwise, we extend the path to every unvisited city and keep going deeper. This class BFS solver is almost the same, but instead of a stack, we use queue using DQ. This means BFS explores paths level by level, unlike DFS, which goes deep. This class solves. Now coming to IDFS, this is a iterative deepening DFS. It runs DFS but with a depth limit. This helper function checks all the paths only up to a given depth. If we find a complete door, we check its cost. We gradually increase depth until we find the full tour. This combines the advantages of DFS and BFS.
Myself Yadu Krishnamma. Today I am going to discuss about the topic travel and salesman problem using hill climb algorithm. For that I import random and time. Time is for how much time take to get the output. It will calculate the time and random for the input. First city maybe randomly we have to choose. So this is the class for the hill climb algorithm. You can see when the object is created, the distance will be assigned to the distance will be initialized, the number of cities and city names. And this left solve is the main function which will calculate the minimum cost and the optimal path. For that, there is a sub functions. Calculate path cost will calculate the cost, and this function to observe will be sap the cities for get the neighboring routes to get the optimal path. So let's test with the four cities and the five cities. So first we initialize the time with 0 and we create the object for the hill climb solver. Then we call the method solve which will give the minimum cost and the path. Uh, so it will help to print the path here, see, and this is the minimum cost. So we convert it into microsecond because the input is small, so we have to do that. and let's run the code to see how the things work. So you can see for the city problem, it takes 25 microseconds and the minimum cost is 18. And you can see the path here. So C is initially randomly chosen. Here is also C is initially chosen. So see the time is 58 microsecond and the cost is 65 seconds. Note that hill climb is not always give the optimal cost because it may point to the local minima. If the input is more and the more cities, it may lead to local minima. So let's analyze the performance of each functions used in the travel and salesman problem. We use DFS, BFS, and IDFS. These three functions, these three algorithms will give the optimal cost. However, the minimum cost, however, the this hill climb will give the may give the local minima. So let's run the code. So you can see the time complexity here. Hill climb is faster, uh, and the cost is 18 for all the algorithms. So consider BFS take more space complexity compared to DFS and IDFS. So best to use DFS, BFS, and IDFS compared to hill climb, even it is a less time complexity because it may not give the optimal one. Similar cases for the 5 city problem also. As the cities increases, better to use DFS and BFS and IDFS. Hill climb may give the local mean. So DFS is more good when compared to the space complexity. Thank you.